Hi, this is an example problem from chapter 23 on resonance in an RCL circuit. Pause for a moment and read the question. Alright, so we're asked to calculate the resonant frequency in this circuit. This is pretty straightforward. I'm going to just chat a little bit about what it means. So, in an AC circuit, we've got some voltage here. That's the AC voltage supply produced by the generator. And that's going to go ahead and drive some current here in the circuit. But these three elements, they all add some resistance to the circuit. And if we lump these all together as a single resistance term, we can call this thing Z, the impedance, right? Resonance means we get the largest possible current in the circuit. So we want this current to be as big as possible. We need to pick the frequency of oscillation here, F0 with the generator, to be on resonance. I'm going to just show you how we come up with the equation for resonance. So let's write down the RMS current in this circuit. We know that that's going to be equal to the generator voltage divided by the impedance of the circuit. Now if I want to maximize the current, we need to minimize the impedance for any given voltage, right? Let's write out what the impedance is equal to. The impedance, we know, can be written as the square root of the resistance squared plus the inductive reactance minus the capacitive reactance squared. How do we make this entire denominator as small as possible? Well, if we can make these two sum to 0, then that whole term will be 0. How do we do that? Set x and L, XL and XC equal to each other. So if we do that, well, let's just do it right over here. Then we're going to say, okay, 2 pi F L is equal to 1 over 2 pi FC. And this is called the resonant frequency. We go ahead and put a 0 below it to indicate that's the resonant frequency. So to calculate the resonant frequency, all we need to do is solve for F here. Let's get a little space. So what we want to do now is get F on both sides. So let's go ahead and multiply by this term on both sides. And of course that cancels this out. And what do we get? We're going to get a 4 pi squared CL multiplied by the resonant frequency squared. That equals 1. We can go ahead and solve for the resonant frequency squared. That's equal to 1 divided by 4 pi squared times CL. And now we're going to go ahead and just take the square root of both sides of this equation. Remember, the square root is a power. So this means that we're actually we're allowed to distribute the square root to all these terms since they're either divided or multiplied. So the resonant frequency, square root of 1 is 1, square root of 2, 4 is 2, square root of pi squared is pi, and then we're left with the square root of CL. So at the end of the day, that's the equation we're going to use to calculate the resonant frequency. Now, in this circuit, we have a value for the capacitance, 1.9 microfarads. Let's make this a little bigger. Micro times 10 to the minus 6th farads. And for the inductance, we have a value of 10 millihenry. So 10 millihenry, that's 10 times 10 to the minus 3rd Henry. We need to take a square root to that term there. And when we do that, we'll end up with the resonant frequency. That comes out to a frequency of 1.15 times 10 to the 3rd And this is going to come out to 1/seconds or hertz. So as long as we're in SI units of farads and Henry, we'll end up with SI units of hertz for the resonant frequency. So there we go.